Good morning. This is Ms. Billerbeck, and we are going to talk about 11.3, interpreting the shapes of data. So symmetric data display, that's data points are evenly spread on either side of the center. The mean approximately equals the median. So this looks like a symmetric data display right here. So skewed data display. So that's data points are unevenly spread on either side of the center. The mean is on the tail side of the median. So if we're skewed left, the tail is on the left, right here. If we're skewed right, the tail is on the right side here. So that's a T right there. All right, so let's take a look at what that data means. So the important thing to take from this is the mean is on the tail side of the median. Okay, that's why it's skewed toward the tail. So we have the histograms show the weights of all dogs entered in 2 different categories in a dog show. What inferences can be made based on the shape of the data? And then we're going to look at another question. What can you infer if a third category had a mean of 40 pounds and a median of 32 pounds? So let's take a look at the data. So we see that in the dog show, we have a mean and a median that are both 45. So this data display includes the entire dog population. It's also very symmetric here. All right, so then on this one, we have the mean is 27. So it's on the right side of the median. And the tail is over here at the median. Or over here on the right, excuse me. So this would be skewed to the right because the mean is on the right side of the median and the tail is on the right side. This data also includes the entire dog population as well. Okay, so with the first one, we have their weights of dogs in 2 different categories. So we have 1 category here and 2 categories here. Okay, so if we had a third category and the mean was 40 pounds and the median was 32 pounds, well, the mean is still greater than the median at 32 pounds. So 40 pounds is much greater than 32. So the mean is on the right of the data. So if we had a third category, it would still be similar to this where the tail is on the right. Okay, but from here, if we actually look at what the data is saying, despite the display of the data, it says that most of the dogs are 40 to 49 pounds, or we could say most of the dogs in this category are 30 to 59 pounds. In this category, we would say that most of the dogs would be between 10 to 19 pounds or 0 to 29 pounds. So it's like very tiny dogs versus very large dogs. And it'd be very unusual to have a tiny dog at this weight. It would need to go on a diet or something. All right, so let's take a look at the questions again. So based on the data, is the first population was a symmetric display? And the second histogram was skewed right. And this would also be skewed to the right because the mean is greater than the median. It's on the right side of the median. All right, so let's take a look at this. All right, we have customers of a bagel shop complained that some bagels weigh less than the amount on the label. After a random sampling of 30 bagels, what can be inferred if they're supposed to be 90 grams each? And how does the skewed data affect the mean here? So let's take a look at the first collection of data. Okay, so here we have the 90 to 94 gram bagels, which is the majority of the bagels. Most bagels will land between 85 and 99 grams, but we do have a few of these that are manufacturer defects over here that could be a problem. So this would be a concern that these customers are complaining validly. Maybe they got some of these bad bagels here or light bagels here. And then again, if your processes created something like this, you'd have to advertise it as bagel lights, a diet bagel. There you go. So anyway, and here we have the mean is 87.7 grams and the median is 90 grams. So this is on the left side of this. So the tail, the data is skewed left. Okay, so this is not good. This means that the customers have a valid complaint that there's a problem. So the manager steps in now. So we are going to, well, first, before the manager steps in, said we should say, yes, the data suggests a problem. And the mean is on the mean is left of the median. So the data is skewed. The display is skewed to the left. All right, now the manager steps in. And he doesn't believe these results. So he does a second random sample of 30 bagels. So here's his results with his histogram of his bagel weight. All right, so the manager can say, ha, it is okay. Look at this. My mean weight is 97.7 grams and my median weight is 90 grams. So I can put 90 grams on my package without a problem. And it's like a bigger dozen. I'm giving you a lot more than what you're paying for. So he does have a low at 85 grams here. So this is his general range of bagels, which is okay. 85 to 99 grams. And there's a tail here with very heavy bagels for 90 grams here. So this data, since the mean is on the right side of 90 on the number line, the tail is also on the right. So the data display is skewed to the right. So if this is the situation with the manager's data, then there's nothing that needs to be fixed in the process at this point. So this data suggests that there is no and the data display is skewed to the right as opposed to the left. All right, but because this is the manager saying there's no problem, the quality manager steps in. So the quality manager says, hey, the customers have a problem. The first data suggests that they are correct. The manager, bagel manager, his data says there's no problem. I'm going to take twice the amount of bagels, and it'll be a random selection of bagels, and I'm going to see what I get. So let's take a look at that data, and let's keep in mind what might happen if we added 5 bagels that are 78 grams and 5 bagels that are 108 grams to this data. So here we have it. All right. So we have the mean and median bagel weights are now at 90 grams each. We have a sample size here, n equals 60. So it looks like we can guarantee a bagel from 80 to 104 grams. But again, our mean and median weights are the same. So this suggests that we had no problem with the process. Our sample size was too small for the first 2 samples, and we needed to take a bigger sample size. Sometimes it's cost prohibited, so we can't take bigger sample sizes. So that's why we don't usually take very large sample sizes, is cost and time and resources. All right, so if we added 5 bagels here, that's 78 grams, and 5 bagels here at 106 grams, would it affect the mean and the median weights? Well, since they're both balanced at 5 here and 5 here, it would not affect the mean and median weights. It would create a larger range of data spread and variance to the data, but it would say the mean and median are the same, so we'd have very symmetric data still. All right, so that's how you would solve a problem using histograms and all this. So what we have here is the process is fine. It doesn't need any changes. And here we have a greater variance of data, but symmetric. Oops, symmetric, there we go. And this was a symmetric data display. All right, our last example is something we should all know how to do, is to look at different statistics for the districts in which we're thinking about working, or companies. So Joshua is considering a job offers from 3 different school districts based on the following histograms about the district salaries. What can be inferred? And then we want to look at another question here while we're looking at the data. If the mean salary of a fourth district's 57,000 and the median salary is 49,000, should be considered that district as well. So let's take a look. All right, so we see at this district, it's somewhat symmetric data. The mean and the median are very similar. They're very similar here. The mean is a little bit to the right. I'm sorry, to the left of the median. So that, but it's very insignificant. So this is very symmetric data display. So this means that the district has a lot of young teachers, and it has, well, it has a few young teachers and a few older teachers, but most of the teachers are in the middle years of teaching, and they're being paid similarly. This one, we have a mean of 48,000 and a median of 42,000. So because this is on the right side of that, our data is skewed to the right. So it says this district predominantly has young teachers and doesn't keep a lot of older teachers around that are paid more. Okay, so that means that your resources for learning from older teachers is limited in this district. Then we have older and more experienced teachers, I should say. More years of teaching is not necessarily associated with the chronological age. All right, so this one we have a mean of 65,000 and a median of 70,000. So the mean is on the left side, which has a tail on the left side. So that means that this district has very few new teachers, and it keeps its older teachers and more experienced teachers. So it must treat its employees better. So that's a very strong indication that there's very little job turnover at this school, which means that the school district must be a very good school district if very few people want to leave that district and move elsewhere. So when we look at the fourth district of a mean salary of 57,000 and a median of 49,000, that looks more like this one, where your mean is over here to the right of the median. So that means that that fourth district is catering towards saving money and hiring teachers with less experience, which they have to pay less than this district, which wants to keep its more experienced teachers and pay more. All right, so let's take a look at what we can infer here. So we can say district, the third district is where to work. It looks like people like working there, they stay working there, so it's skewed to the left. So let's take a look at that one more time. No, it's the third district right here. Yes, it's skewed to the left because the tail's on the left. Okay, you don't want to work for District 2 because it's skewed to the right. Second district hires younger teachers or less newer teachers. And skewed to the right. Okay, So let's take a look at that one more time. So that one. So this is skewed to the right. We've got a bunch of new teachers in here that are paid less. So there's fewer resources for you to learn from your peers versus this group. Wow. District 3, you've got a lot of resources to learn from your peers. Okay, this one is just a good district. There's nothing wrong with having a symmetric data pool. So my choice I wouldn't rule out District 1. It has a lovely symmetric distribution where it keeps most of its teachers here, and it has new teachers, and it has the highly experienced teachers over here. So there's a wealth of knowledge of learning from your peers in District 1 as well. Okay, so this one here, if we have a mean of salary of 57, that's a skewed to the right. I wouldn't consider it. It has, because it's hiring just new teachers, it's not keeping its older teachers. It's skewed to the right. So there's a lot you can learn from looking at data displays. And you can learn it in a very short amount of time. That's why statistics is so important. All right, that's it for today. Have a wonderful day. Bye-bye.